I'm very glad here to share our thinking about AI platform. As you all know, machine learning has become a toolkit that is easy to reach out for every startup company. But what makes AI powerful is not a typical model. It relies on efficient iterations in the AI workflow, including preparation, build, and deployment. Meanwhile, the recommendation system acts as one of the most important AI scenarios. So it's inevitable to deal with many handshakes with the platform. So today's talk, we will be talking about AI platform and the recommendation system implementation in SHAREit. We will talk about this AI workflow and how we face it. Okay, here is an introduction. An introduction about SHAREit Group. SHAREit Group is dedicated to building high-quality content platforms that it connects users and content globally. Our diversified suite of applications, including our core app SHAREit, have been installed by nearly 2.4 billion users worldwide. The business network has reached up 150 countries and regions in 45 different languages. And SHAREit was recently ranked as the second top Southeast Asia headquartered applications publisher worldwide for 2020 by App Annie. So in short, SHAREit is an app that delivers all kinds of content, pictures, videos, and apps. We serve users globally, and we have hundreds of millions of monthly active users and diverse big data scenarios. Oh, this is a picture of younger me. My name is Marshall, and I'm located in Beijing. I'm the big data director of SHAREit. From a technical view, I focus on data and AI, and I have worked on it for nearly 7 years. I have two interests. One is data and AI democratizations. The other is multi-cloud hybrid architecture. From a business view, I'm familiar with user groups and advertising. There are three groups of my team. First one is data infrastructure, including compute and storage. The second one is data platform and production. They engage to democratize data and AI. The last one is data warehouse. They facing data pipeline requirements, and they support data analysts, data scientists, and algorithm engineer or machine learning engineers. Oh, sorry. I found there is some time latency during the Zoom meeting, so maybe I will stay for a few seconds between the pages. Okay, this is today's agenda. When we talk about database powers AI, what we are looking for is the entry point. This talk takes AI workflow as the insurance and introduce the whole topic from the demand, conception, implementation to application. Corresponding to these 4 steps, a more practical description is about demand is equal to what hurts the most. The next is conception. Conception comes from our combining and the understanding of the current situation. Implementation, I will describe a locally adapted AI platform, especially focusing on Featurestore architecture. As for application, I will take the communication between the recommendation system and AI platform as an example, and our thinking and practice on TiKV and TiDB. Okay, let's start from demand. Conception and implementation came from the current pain points. Through researching actual frontline colleagues, we found that the biggest pain point now is that algorithm engineer or machine learning engineer spends too much time doing non-algorithm work, which makes algorithm engineers less AI. Let's look at the table named time consumption. First of all, the time consumption is roughly divided into 3 parts. The data preparation. the data preparation takes up 50% of the algorithm engineer's time. And this process not only involves itself, but also involves the data engineer. The second one is model training and strategy development. This work are their own job, but due to the current weak standardization, it also involves interaction with system engineers. Finally, the deployment. Although the time not too much, it must rely on the scheduling of the system engineer. So the slow pace leads to lower efficiency and higher risk. Based on their descriptions, we have found and we have obtained several information. The first one is that a rough split of AI workflow, and the second is there are 3 roles: data engineers, server system engineers, and the algorithm engineer itself. And I draw some pictures next to the table. You can see these 3 roles. Starting from this page, our introduction will focus on this workflow, this AI workflow, and these 3 roles. Okay, let's look at the flow chart below. No, everyone is unhappy in every step. The main reason comes from these problems. For many startups, AI is within reach, but the data platform and the metadata governance are often incomplete. Therefore, algorithm engineers often ask the above questions, such as where is data source, how to extract features, how to build a pipeline. Therefore, algorithm engineer and finally they have no choice. Finally they have no choice but to ask help from data engineer. It is difficult to avoid using GPU resources for model training, but distributed GPU training is not available out of the box. So the assistance of a system engineer's colleagues is very required. In addition, algorithm engineers often use Python, and the recommendation system is written in C++ or Go. Logical translation is really a headache. The next section, deployment. Deployment as an algorithm engineer, they can do nothing but wait. I believe that this difficult position is an inevitable stage for most companies, and how to make this stage more smooth and short. So we had to deep into. Let's move to the next page. Okay, this is conception. A conception is equal to our understanding of current situation. So when we refined the rough steps we talked about, we found that the current workflow is inevitable serial, but the main problem is that the efficiency of each step is very low. Let's pay attention to the flow chart. The process is from left to right. Okay, it is still the AI workflow, and we divide each step into several detailed processes. We use colors to identify the roles required in every process. Now you can see, after zooming, almost all processes need more than one role, and too many dependencies lead to endless communication. Every R&D firm should have the same experience. Dependencies and communications often bring efficiency problems. Every R&D firm maybe want to coding quiet. Let me introduce the noun and our definition first. Operators rejection and features rejection. Features as the attributes or properties modules used during training and inference to make predictions. For example, when recommend a video list, features including video categories, user age are very useful. The generation of the feature includes the selection of the original fields, the operator, and the target feature name. Our operator rejection is equal to writing a unified method. And the feature rejection is to combine original fields, the operator, to complete a feature. The operator rejection is currently being developed by the system engineer because it is written by C++, and it's also our own problem, our typical own problem. And the feature rejection is a data engineer because it involves the complex modification of ETL codes. The sample generation process. The sample generation process is sampling is very important and common in every machine learning working flow. So this process is currently being developed by the system engineer because it is the sample. The sample generation process requires frequent communication, and the data engineer and the algorithm engineer will work together to accomplish. And the model training strategy development, the strategy development and the deployment are all the same. And there are 3 service goals here: feature extraction, inference, and monitor. You can find that the entire workflow is conforms to the AI paradigm of AI regulation. However, the core time-consuming steps are caused by insufficient standards and frequent interactions. Therefore, we divide every step into many processes and to solve each problem separately. Okay, let's move to the solution implementation. In the stage of rapid business development and explosive needs, it is very important for us to win long-term and short-term goals. So we build the platform on a broad set of capabilities that we already have. During this period, we have 2 principles. First one is build production line through integration. The production line is very important for efficiency. Second is divide and conquer. First, build production lines to elaborate the labor force that currently supports business requirements, and then focus more on the improvement of each module. Of course, we also learned about some commercial products in the industry, such as AWS SageMaker. I believe everyone heard about it, and Databricks has its own product. Yeah, before launching our own AI platform, we have tried many times, but SageMaker bases on a series of standards, and we just use some modules. And there are still some specific requirements that it didn't support. So it is very difficult to do some migration from our system to the SageMaker system. I think it is a common issue for every startup companies. So we designed our own solution. We have 4 modules. Let's look at the picture. We have four modules. And these modules cover all the machine learning workspace. After these modules, I believe every machine learning engineer will happier. Yeah. First one is Featurestore. Featurestore solving data preparation problems. It composed of online storage and offline storage. Later we will discuss it deeply. The second one is training pipeline. Training pipeline provides templates for training and strategy development. And this kind of template is mainly composed of some Python modules. Serving framework, the interaction with the application side. And the most important application is the recommendation system. The last, deployment and test. Deployment and A/B test are natural important processes for all iterations, not only in machine learning. These modules bring us 4 advantages. Firstly, feature sharing, feature meta information sharing, and we will reuse feature pipeline to reduce the compute cost. It is very important, especially on these days we all use cloud. Secondly, sample pool management. It can diversify the use of data, speed up calculations, and optimize costs. Thirdly, model training, model management, automatic resource allocation. and improved model training efficiency. The last is deployment. And there are still this service, feature extraction, inference, and monitor. Okay. Let's deep into the Featurestore architecture. It is very clear to see Featurestore is composed of two links. The first one is the online streaming link. The online storage, the low latency, high availability cache for features group that enables real-time lookup of records. It is usually used for serving online service. We collect client logs and server logs to Kafka topics. Then we use Flink to accomplish streaming computation, output raw fields and indicators, and write it to online storage, serving the real-time inference. In other words, the real-time inference is the recommendation service. We currently use self-developed KV for online storage, named Sharestore, and we will gradually switch to TiKV. As the flow chart shows, write and read QPS is very high, and the demand is very strict. The second is offline data stream, offline storage. Offline storage stores lots of historical data. It is used when offline feature exploration, model training, and batch inference. Sorry, wait a second. Okay, let's restart with offline storage. Raw data sync to data lake from Kafka. Then we use Spark to generate raw indicators table through hourly and daily merge. The raw indicators table is very important. Next, after feature extraction, a feature table is generated based on the raw indicator table and the feature table. Algorithm engineers will generate their own sample for offline training, and these samples belonging to the sample pool. We supply the sample pool management. Throughout the pipeline, we are advancing modularized SQL to describe business logic, and at the same time implement version control through the slot mode and the data lake technology, such as Iceberg or Hoodie. After talking about online and offline storage, let's move to the online and the offline school. We use the same Git repository to write the feature extraction code, generate a C++ shared object file and the configuration file. All feature extractions will use this package to solve the online and offline school. Okay, let's talk about the application. After talking about the main Featurestore architecture, let's think about the application. Needless to say, the main scenario is recommendation. Regarding the recommendation architecture, its paradigm is very mature, from recall, cost ranking, re-ranking to mechanism turning. Here we will focus more on the intersection of Featurestore and the recommendation system. This is also where we face more challenges and how TiKV and DB help us. In SHAREit, we have two scenarios involving recommendation. One is the content side, and the other is the advertising side. We use a general recommendation architecture to support all these scenarios, including model server to complete the recommendation workflow, and the prediction server to complete the CTR or eCPM estimation. In content scenario, we pay more attention to the timeless of user behaviors feedback. Client events are returned with a delay with some time latency. So we have a strong demand for streaming compute. In the advertising scenario, because of the huge amount of traffic, one request will involve a large amount of feature readings. So these scenarios are very strict for our KV or DB selection. Initially, we thought of Flink and general keyway. For example, a new user uses the feeds flow, and we hope to recommend the new contents based on the operations on the first screen within 5 to 10 seconds. At the same time, we also think about DB, because the SQL interface provided by DB not only can improve the efficiency of development and maintenance, but also lay a solid foundation for standardization and automation. These are two parts that's how TiKV and TiDB help us. Firstly, the online storage interactions with recommendation system. Some number of status is on the picture. Online storage is a usual way to use keyway. And the secondly is what we are planning now, or we are doing now. Online learning. Online learning is very popular nowadays. So we plan to try some online learning. See whether it is have a lot of benefits. So online learning there shows a simple flow chart. Online machine learning is a method of machine learning in which data becomes available in a sequential order and is used to update the best predictor for future data at each step. Simply saying, using incremental data which containing user impressions and clicks to enhance the older model. So we tend to call it combined storage, belonging to Featurestore. We tend to call it combined storage, because if the data merge and the feature extraction mentioned earlier can be finished in the streaming way, based on the adjustment of the window, we can combine the streaming and the offline computation processes into one, and sync data to the lake through hourly scheduling. Therefore, it is not only online storage, but also solve the complex offline logic problems. So why we use TiKV or TiDB? First of all, in the online storage scenario, we had a self-developed KV we talk about, and we invested a lot of human resources to this self-developed KV. We plan not to build wheels at the bottom, but use the power of the community. As for online learning, we hope that the storage can support high concurrency streaming rates. At the same time, on the read side, it involves a lot of business logical descriptions. And we hope to lay the foundation for future automation as much as possible. So it would be better if there is a SQL interface. If not, the logical description in Flink will inevitably become complicated. So our online learning hopes to train the sample in 5 to 10 minutes, in every 5 to 10 minutes. According to the amount of data latency can be trade off. So after the test, TiDB is considered a reliable choice. Okay, let's move to the next page. Stand on TiKV's shoulder. When we first investigate, we found that TiKV as a general KV story is something we need. We decided to embrace open source. At the same time, we also hope to abstract some of our internal experience and contribute to the community. So we stand on TiKV's shoulder. There are two main work. The first thing is to support multiple types at the proxy layer. You can see on the picture. For example, site, this site, hash, and the counter. This is actually a recommended requirement. In addition, as a storage role, KV interacts closely with the big data ecology. And in these scenarios, they often require batch input and batch export of data. Through this realization, we integrate TiKV or TiDB into the data and AI pipeline. Afterwards, users do not need to worry about storage choices. These two works we are doing now. Okay. All right, that's all for today. In summary, how DB powers AI. Let's look at the table. So there are some data disclosure in these two parts. we talk about online storage and online learning. The storage level is TB, and QPS is higher than 50 seconds. And on online learning, each window is 5 minutes. And after what we have done, the 50% cost decreased to 25 or less during the workflow, during the AI workflow, which make algorithm engineers happier a lot. Today, when the big data paradigm is clear, users are often affected by the empirical thinking of the scenery. However, we divided the scenery into several demand points first. According to the different quantity needs, discuss and combine our new solution. The usage of DB bring us some new angle. Single link latency is very important, but if interface can lay the foundation for subsequent modularization and automation, it will be more beneficial to the iterations. So we choose DB to support our online learning scenario. Meanwhile, in the stage of rapid business development, we divided and gradually delivered the big plan, which also won more resources for our long-term tasks. Okay, I hope to be useful for everyone. Thank you. That's all for today.
Thank you, Marshall. That was actually a really excellent presentation. We really appreciate it. We do have a couple questions that came in for you. Do you mind answering a few questions before we finish?
Mm-hmm.
Okay, great. So listen, the first one was, can you tell us a little bit about the advantages of TiKV as compared to say like Redis or Redis persistent cache or the Redis cluster?
Okay, all right. In online recommendation scenario, okay, I chose online recommendation scenario to explain this, to answer this question. Sure. In online recommendation scenario, a request often involves a large number of feature queries, and some features are also of large value type. So Redis is not work in every time. First of all, TiKV, a general purpose KV, it provides us with stable performance compared to Redis cluster, and it is easier to integration and interaction with the big data ecosystem. The last and most important thing is cost, which is a very significant cost down action using TiKV to replace Redis.
Mm-hmm. Okay, great. And my second question is, so why are you using TiKV instead of TiDB? I mean, you mentioned both at some points in your presentation, but you focused on TiKV. Why did you choose that one?
Mm-hmm. We have talked a lot about this using TiKV or TiDB. Still in the recommendation scenario, yeah, we have high requirements for latency, and the complex logic is generally implemented on the server side. Therefore, we hope that online storage is a simpler KV, and the added benefits provided by DB cannot be highlighted in the online storage scenario. But on the other side, in the online machine learning scenario, the DB's SQL interface is very worth to try. So we choose TiKV or TiDB in different scenarios.